Cool. I think we're just going to get started. It's been a few minutes after now. Welcome everybody to yet another mass timber meetup here with Tallwood Design Institute. I am Evan Schmidt. I'm your usual host. For those of you who don't know, I am the outreach coordinator at Tallwood Design Institute. And this is a kind of a recurring event that we put on mostly through the fall and winter months. For those of you who aren't aware, this is really a kind of casual peer-to-peer learning platform that we've been doing for a while. And the goal is to get a couple of panelists together to chat about something related to mass timber, whether it's acoustics or fire or structural engineering or a project, and then to discuss it afterwards. So today we're being joined by KPFF engineers. Specifically, we're here with Reid Zimmerman and Jack McCutcheon, who have actually given presentations previously. Last fall, they gave a presentation on mass timber lateral force resisting systems, which was really great. I'm going to post a link to that in the chat after I hand the microphone off to these guys. So if you're interested in seeing that, you can get a chance to look in the chat. And today we're going to be talking about floors for walking-induced vibrations. And so before I hand off the microphone and let you guys give your presentation, just want to give a shout out that we're going to be posting our fall meetups early. Usually I used to just wait until one meetup was done before I posted the next ones. I'm just going to start posting them as they come from here on out. So if you go to our meetup group, you can see what is coming. So far, we've got a meetup with Aspect and Bethune on September 9th, and they're going to be talking about a modular mass timber housing project. And then we've got Dan Tingley from Wood Experts, who's going to be talking about timber bridges. And that's going to be kind of an interesting one. They're actually international organization, but they have a facility in Jefferson, Oregon, just south of Portland, where they design and manufacture and fabricate timber highway bridges. So he'll be talking about work they do. So check that out. We probably will have a few more coming this fall as well. So just keep your eyes peeled. And yeah, with that, I'm just going to hand it right off to you guys. So thank you for being here and looking forward to seeing your presentation. For those of you who aren't familiar, we're just going to wait for the presentation to be done before we ask any questions. You can feel free to put questions directly in the chat and we'll kind of moderate it at that point. Or you can just wait and ask them directly when the presentation's over. So, Reid, take it away.
Thanks, Evan. Yeah, so, and all for having us. And so Jack and I are going to talk about today design and mass timber floors for walking-induced vibrations. And we're really going to build upon or build from the U.S. Mass Timber Floor Vibration Design Guide. It's a WoodWorks document that was recently published that both Jack and I participated in, and just acknowledge our collaborators on that design guide, which are listed here on the right. It was a significant effort, really growing out of the idea that, at least for steel framed floors, we have in the United States AIC Design Guide 11, which provides some good guidance on this topic for steel framed floors. And there are similar documents for concrete floors, but really there wasn't anything that existed for mass timber buildings. And I think those of us who design with mass timber recognize that the floor systems are often governed by vibration rather than strength or deflection. So outline of our presentation today, we're going to go over a bit or very briefly about vibration sensitivity and subjectivity and sort of why this is an interesting topic. I'll have to walk you through a bit of the vibration theory, so hang through it with me. And then I'll pass it over to Jack. He's going to talk about human and equipment sensitivity to vibration. He's going to talk about some of the decisions and effects of that you have in sort of control that you have in the design process for mass timber floors. And then a lot on the design methods and modeling of mass timber floors for vibration. I'll jump back in and talk about a few design examples which exist in the WoodWorks document, and then a little bit on in-situ testing and where that's leading us to and how that's informing our mass timber design. So vibration sensitivity and subjectivity. The first thing to note is that, at least in the US, vibration is not a code requirement. It is something that is very felt by the building occupants. It's very important as a design criteria, but it is, especially for mass timber floors, but it's not currently codified. And this is, Jack and I were actually out testing at a building, and I looked over as we were testing, and this little bobblehead was there. So I'll show you a quick video. I think this illustrates exactly what we're concerned about for vibration. So you're sitting at your desk or you're sitting at your microscope and somebody walks by, right? And your head, in this case, starts bobbing. The floor is basically bouncing, and it's not a safety concern. Usually it doesn't cause cracking or damage. It's about human comfort, mostly about human comfort. Sometimes in higher performance facilities about what we'll call like equipment comfort or equipment sensitivity. So it's hard to represent vibration in this virtual platform. So what I'm going to do is I'm going to play some sounds for you of different frequencies, and we are going to bring it back to kind of structural vibration here in a minute. So you don't have to understand necessarily that figure, but just know that I'm going to play for you two sounds. One's at 1,000 hertz or 1 kilohertz, and one's at 100 hertz. And I've picked the two sounds that, at least to me, they sound what we'll call equal loudness. So kind of equal intensity. Here's the 1,000 hertz. Can someone just confirm they can hear that? Thanks, Jack.
Yep.
So, okay, here's the 1,000 hertz again. And here's the 100 hertz. So to me, those sound what we'll call equal loudness. But those are actually different amplitudes. They're not equivalent amplitude. And that's something that the human ear hears frequencies differently. So if I were to play for you, which I'll do next, two sounds that have equal amplitude, this is what they sound like. Here's the 1,000 hertz, and here's the 100 hertz. If you can even, depending on your speakers, you might even be able to hear the 100 hertz. The 100 hertz is significantly less loud, even though they are the same amplitude. So we've got some kind of curve here where, depending on the frequency, we hear things differently. This is that same curve, but now for vibration. So you notice on the horizontal axis, it's still frequency, it's just a different scale. Instead of in like the 100 to 1,000 hertz, it's in the 1 to like 30 hertz range. But we see that same relationship of kind of different sensitivities to different frequencies. And what that is in structural vibrations is actually on the right there is sort of a very engineer's model of a human, but representing different parts of the human body and really our abdominal mass. Some of us more than others, our abdominal mass has a different frequency, really in the range of that 4 to 8 hertz. And so that's what we feel. We're most sensitive, meaning we can feel vibrations in the 4 to 8 hertz range most easily. The problem with that is that most floors are in that really 6 to 10 hertz range. So we're kind of overlapping our design space with the most sensitive region for human comfort. So a bit about the theory of vibration. Here's like a single degree of freedom system that most of us have seen. It's a mass with a stiffness. If we pull on that mass and let it go, it goes into free oscillation. There's kind of, the period or the frequency. The period is the time between two instances. The frequency is the inverse of that. There's some amplitude, like we talked about with sound. Usually in vibrations, we're measuring it in terms of acceleration. And then, there's this relationship between the stiffness, the mass, and the frequency. So this is really important when we're thinking about design decisions in mass timber. In addition to sort of the straight amplitude, there's this thing called RMS, or root mean square amplitude, for a sinusoidal wave that's just the peak amplitude divided by square root of 2. That's important when we're doing kind of measurements. And often really, people aren't sensitive to that peak amplitude. They're really sensitive to more like an average, or in this case, RMS amplitude. Additionally, floors are not single degree of freedom systems. Even a single beam, a simply supported beam, has 3 modes. And if you're talking about a multi-bay floor, it has many more modes than that, which is represented on the right. So we have to appreciate the multi-mode behavior too. And then, people weigh different amounts for one, and they walk at different speeds. And they walk at different speeds depending on where they are in the building. If you're walking down a corridor, you'll walk much faster than if you're walking in and amongst kind of desks or in your own residence. And so these walking speeds become important as they relate to the frequencies of the floor. So kind of one of the last major concepts I want to talk about, and this is really setting the stage for the rest of the presentation, is that of harmonics. And so let's take the example of having a 6 hertz floor. It's a floor that if you just let it vibrate up and down, would vibrate at 6 hertz or 6 cycles per second. If you were somehow able, even the fastest man alive or woman alive can't run at 6 hertz, but if you were somehow able to run that fast, you would be stepping, like this is showing the movement of the floor, right? You would be stepping at each time the floor was coming up. And so you would really be like reinforcing the floor. That would be sort of resonance, right? But that's the first harmonic. But that happens too if you're, say, able to run, which people are able to run at 3 hertz. Now you're taking every step you take is every other vibration of the floor. And so you're reinforcing the floor, not every single time, but every other time. That's the second harmonic, and so on. If you're walking, you're hitting every third. You could be walking at 2 hertz, you'd be hitting every third. That would be the third harmonic. And if you were walking at 1.5 hertz, you'd be hitting the fourth harmonic. So what's interesting about it is you could walk at 2.2 or 2.4 hertz, and it could actually have less effect, less vibration than someone walking at 1.5 hertz, because you're hitting different times in the natural vibration characteristics of the floor. So these harmonics become important when we're trying to understand floor vibration. And then, if we talk about a low frequency floor where you're reinforcing it every single time, and that vibration is building up, or we're talking about a high frequency floor where you step, the floor has a long time or in relative terms, the floor moves a bunch before you take another step and decays because there's damping. This really matters for later in terms of how we calculate resonant versus transient governed floors. And really this 8 to 10 hertz is that transition between the two. And that becomes because that harmonic, that fourth harmonic, basically that fourth harmonic times a walking pace of 2 hertz gives you 8 hertz. That's why that transition happens. If we happen to be able to walk faster, then our floors would need to be that transition from the resonant transient response would also move up. And then obviously damping helps to a degree. We'll talk about what you can do in terms of damping. Okay, last thing on theory, and then we'll move in, and this will move into more application, is typically we're looking at things that are in red, acceleration versus time. So the shaking that's happening versus time. A convenient way to look at it in terms for vibration is actually not in terms of acceleration versus time, but in terms of decomposing that acceleration history into the sum of a bunch of sinusoidal waves. And this is called the Fourier transform. We don't need to talk much about it, but basically the way we can represent that acceleration history that is very chaotic in terms of the amplitude and frequency of a bunch of different sine waves. So in this case, that one acceleration history in blue there on the left can be represented by 2 sine waves, the green and the purple of those amplitudes. And that's kind of what that spectrum looks like the foyer spectrum looks like. Again, becomes important later as we talk about kind of analysis and testing. So now I'm going to pass it over to Jack to talk about human and equipment sensitivity to vibration.
Yeah, thanks, Reid. Are you seeing my screen here? Thumbs up, great. So assuming we're designing a building and a floor plate, the first thing we need to understand is what type of performance criteria we need to design for. As Reid explained, our human perception varies based on frequency. It also depends on what type of occupancy that the building is intended for. And there are no code requirements for vibration design, but there are best practices. The most well-known here in the US is the ASC Design Guide 11, intended for steel buildings, but the design criteria is translatable to all building types and materials. In that document, it has this nice curve here on the left. Most of the time we're dealing with typical buildings that are offices or residences. They're going to live in that 5 to 10 hertz fundamental structural frequency. And we're going to be targeting a 0.5% G acceleration limit criteria. Other buildings, maybe like pedestrian bridges, shopping malls, airport terminals, things like that, might have a little bit more lenient design criteria. Premium offices may have more strict criteria. And then as we move to more higher end facilities, such as hospitals, labs, these are going to be more high frequency floor systems controlled by the transient response. And these are going to have criteria established within that RMS velocity limit. And these numbers here are in MIPS, or micro inches per second. And that's a velocity target. And that can vary widely depending on what type of use this floor is going to be seeing, whether it's just for hospital patient rooms or really high-end microscopes. So it really depends on the use. The Facility Guidelines Institute also has a document out which outlines recommended design criteria for hospitals, depending on the area of use again. But it's really important for us in design to understand what the owner developer expectations are heading into a project, so that we can ensure that the floor system that we're designing, whether it be with timber or even another material, we're designing our structure to meet their expectations, while not throwing a ton of structure in unnecessarily cost at achieving higher performance targets than they actually need. So now moving from kind of what the criteria is into some of the basic theories and design decisions that we have. Essentially, there's 4 variables that we can play within our design. There's stiffness, mass, damping, and what we call vibration path. I'm out of order here, but so the stiffness, I guess, is the first one, and I think it's the easiest to wrap our head around. As you increase the stiffness of a structure, it's going to decrease the vibration response. That's explained here with this equation, where we have K, our stiffness variable, on the numerator side of this equation. So as this goes up, your fundamental frequency goes up, your vibrations go down. The next variable we have is the mass. Sorry, I'm out of order here. Is the mass. That kind of has the opposite effect. As you decrease the mass, that will then increase your floor natural frequency and decrease your vibration response. That's really only true though with resonant response dominated floors. It can have the opposite effect if you have a transient controlled floor. With transient controlled floors that are really high performing office lab spaces or hospital or lab spaces, you need a lot of mass and stiffness to get that high achieving floor rating. And then the other variable we have to play with is damping. As you increase damping, vibration is going to go down. We don't have a lot of control over adjusting damping. That's kind of a fundamental property of whatever building material you're using. Thankfully, mass timber tends to have more inherent damping than other materials. One of the best ways to increase your damping is by having full height partitions between floors, although that's a lot of the times it's not architecturally desirable. And then the last thing we have to play with is vibration path. So you can see here on the figure on the bottom right. So say you have a multi-bay system. You have a hallway in the center of one bay that's causing your structure to become excited. That might result in excitations in the adjacent bay where people might be working or sitting, more sensitive to that vibration excitation. If you were to move that hallway to, say, a support point on the structure, it would reduce the amount that the floor is being excited and reduce the perceived vibrations for that adjacent area where people are working. So what's unique about mass timber, right? So I mentioned that it has a little bit higher damping values, but what can work against us is the lightweight nature of mass timber compared to other materials. So because it tends to be lighter weight, we need less stiffness in our structure to meet code-defined deflection requirements. That can lead to structures that are more susceptible to vibrations. And when we get to larger and larger bay sizes with mass timber, we're often controlled by the vibration design. The vibration design will govern member sizes, maybe topping slabs, things like that. Getting into some of the specifics with mass timber and floor vibration design. In the new design guide document, I included this little flow chart here as a tool for designers. Assuming we've got a fairly regular structure, we're evaluating for response to human walking, and we have our performance criteria identified. If the structure is a simple CLT panel supported on bearing wall systems, we can use the handy CLT handbook method. This is a empirically derived method which identifies span limitations for bare CLT panels supported by rigid supports, so bearing walls. It's really intended to keep the panel's fundamental natural frequency above 9 Hertz to ensure that the resonant response is not an issue with the design. It's really handy for identifying kind of rules of thumbs for span limitations on various panels. So for example, a 3-ply panel, that 12 to 13 foot range, it's kind of the maximum spans there. Further for 5 and 7-ply panels, obviously. But where this methodology kind of falls apart a little bit is if you have supports that aren't rigid. So a post and beam structure with CLT floor panels. It also doesn't do a very good job of accounting for the effects of toppings. So if you have a concrete topping, that adds either a lot of mass or stiffness to the structure. You probably want to look at other methodologies. So we go back to that flow chart here. And the alternate way of performing this analysis, a little bit more in depth, when you have unique geometry or effects of topping slabs, is to use the modal response analysis method. So with that methodology, it was originally designed by Arup and is outlined in the CCIP 016 document. It's a publication out of the UK developed for concrete structures, but the methodology can be applied to any type of material. I won't kind of dig into all the equations here, but in essence, what we're doing is taking the modal properties of the floor structure, using these equations to post-process and predict the floor accelerations or velocities compared to different walking frequencies. So ultimately, you end up with this plot here of accelerations versus walking frequencies, and you can evaluate the predicted response. As a similar set of equations for the transient response. Here, again, where you're plotting RMS velocities in microinches per second against walker frequency. But in order to kind of use those equations, you first need to develop your analytical model to produce the modal results of your floors. And to do that, as engineers, it's more of an art than it is a science. We typically need to assume a different set of criteria for modeling for vibrations. So for example, we would want to use the most accurate material stiffness rather than the lower bound stiffness than we typically use in design. We want to model connection fixities as accurately as possible. So it's really more about being accurate and capturing the realistic behavior of the floor rather than being conservative for a strength or deflection level design. When we're modeling our floor plates, our go-to software in our office is SAP. This is a finite element modeling software where we can input all of the columns, beams, walls, floor decks to really get a realistic behavior of how this floor system is going to behave for low level vibration excitations. Getting into some of the modeling techniques and recommendations, the design guide document does a much better job of this, but I'll just touch on some brief topics. When modeling the floor panels, we want to ensure that they're modeled as completely fixed with the supporting beam structure. And then depending on how connections are detailed, typically we approach beam to column connections, beam to beam connections, and column to column connections all as fixed. Again, that could vary depending on the specific detailing you're using. Floor panel to wall panel connections might be either pinned or by using a joint spring. And then floor panel to panel splices, I think in an ideal world, we would model those with a moment and axial release between panels. But oftentimes in practice, that's often neglected just because it adds a lot of complexity. And also joint locations aren't always known early on in the design process when this work is completed. Another big variable that can impact the design is the effect of topping slabs. So particularly if you have a concrete topping slab over a CLT or MPP panel, accounting for any partial composite action of the topping slab, is really important for the design. Even if the concrete topping slab isn't designed to act compositely with the structure for strength or deflections, it will likely have some type of composite action for vibration level excitations. That can really depend on what type of detailing you have, whether you've got screws between the slabs, for example, whether there's an acoustic mat or a vapor barrier. It'll really affect the design there. And then because CLT is an orthotropic material and behaves differently in each direction, we typically like to model our floor shells as an isotropic element and then apply a stiffness modifier in each direction to that shell element within SAP. And that allows us to really accurately capture what we think that floor will actually behave like. Here's just an example screenshot of what a modal, deflected mode shape might look like for a typical floor plate. This is the result of everything that goes into that model. We get the modal results and are then able to export that to a post processor. In our office, we've developed some Excel sheets, which really help with this, running it through those equations that I showed before for both the resonant and transient response analyses. In this post processor, we're able to adjust things like walker weight, walker frequency of interest, as well as damping ratios. Ultimately, what we're trying to predict here or get out from the analysis are these plots, again, of the accelerations and velocities. So by looking at these plots, we're able to see if there's any peaks within our walking frequencies of interest that are above our design criteria. If they are, then we revisit the design, adjust some of those parameters, whether it be increasing the structure stiffness, modifying the topping slab mass, or composite action with the structure, and then redoing this analysis to then see if we're below that threshold and going through that iterative process until we reach a design that meets our criteria. One of the really cool things about this analysis process and this methodology is that we can analyze a excitation, any combination of excitation and response nodes on the floor plate. So what we're seeing with this plot here is an envelope of results for all of the different combinations of excitation and response nodes. This gives us an idea if there's any little hot spots on the floor which exceed our original design criteria. That way we can tailor any adjustments to the design or framing just for those specific areas. I think with that, I'm gonna turn it back over to Reid.
Jack. So I'm going to talk about the 3 design examples that exist in the U.S. Mass Timber Floor Renovation Design Guide, and then reference you to them for further reading. So the design example 1, we sort of structured the design examples to try and fill the space of typical mass timber floor systems that we're seeing in use today, and some I think that are, I guess that would be the first 2 design examples, and the third design example is trying to see if you had to design a mass timber floor for a much higher vibration threshold or criteria than we're typically seeing for office or residential. So this first design example is the classic CLT on bearing walls. And so this is one where the CLT handbook method applies. And so you'll see in that design example in the design guide, use of the CLT handbook method, as well as use of the modal response combination method, and sort of comparing, contrasting how well the CLT handbook method does specifically for an application where the CLT handbook method applies. So using the CLT handbook method, but then kind of cross-checking it against the more sophisticated modal combination procedure. It also goes through looking at single span versus multi-span and how that makes a difference and how that changes. Jack talked about this idea of sometimes you might want to separate the vibration path. You might want to separate the two spans into individual single span panels so that you don't get as much translation of that vibration across the two bays. There's some cases where many cases where you would want to keep that continuous and utilize that additional stiffness. This design example goes and uses diluable RFM, which is another commercially available software. Not used as much, used definitely much more in Canada than in the United States, with many applications in the US as well. And it shows, again, detailed resonant and transient response calculations. So if you're kind of doing this for the first time, you could essentially try and replicate any of these examples. The next example is one of sort of post and beam, but this time using NLT or nail laminated timber. So the CLT handbook method, as the name implies, doesn't apply for use with NLT or dowel laminated timber, but that is still used here just as a comparison. This example also goes through looking at what the effect of modeling versus not modeling or neglecting the non-structural exterior walls have, which is in many cases very significant, even though typically exterior walls which are non-load bearing are slipped for live load deflection under vibration level movements or vibration level forces. They typically do not slip, and so they do act not exactly as like a fixed point, but they act more as like a spring. So in the design guide, we recommend that any fixed full height partitions, ones which aren't going to move within the life of the structure, and exterior walls do have a modeled spring in its place that will significantly improve the vibration performance. And then the last example is one where looking at the use of mass timber, specifically CLT on a glulam frame for a laboratory like vibration criteria, so very high threshold, and goes through the detailed calculations specifically of the partial composite action between concrete topping and CLT, which is a in-depth calculation, but has again another thing that has a big effect on predicting vibration performance. So last topic for today is just talk about in-situ testing. I think one of the things about mass timber and floor vibration, the intersection of the two, is that we're still in the infancy of our understanding of mass timber floors for vibration, and particularly how to design them well and how to predict true performance so that we are not overbuilding for vibration design. And the way really to do that is to have in-situ tests or tests of built buildings. So we KPFF have vibration equipment and have been going around and testing our buildings and comparing them against some of the analytical models. We don't have all that to share today, that comparison that's forthcoming still, but I'll at least tell you kind of a little bit of what we've been doing. So that picture on the right, that was Jack and I on the roof of one of our mass timber buildings. You can see Portland downtown there in the background. And this is our setup. So we have basically a laptop, this data acquisition system, which is quite small, and several accelerometers, which we place on the structure. And we're really gathering accelerations, but we're able to post-process back in the office, velocities, displacements. We can determine the frequencies of the floor, and we can determine damping of the floor. So all the inputs that we really need to compare against the analysis. And lots of applications of this, outside, maybe a little bit outside of mass timber, but when replacing hospital equipment, oftentimes floors need to be evaluated for their vibration performance. So doing it in situ is the best estimate, obviously. If you're having complaints from your occupants or tenants about floor vibration, again, it's subjective. So you want to try and take it out of the subjective realm and into the quantitative realm. What we've been using a lot for mass timber, which is calibrating our analysis models, and also in some cases where we need to verify retrofits schemes for improving the floor performance. So here's just a quick video of a couple of the tests we do. It'd be nice if we could do them in person, but barring that, Jack and I created these little videos of what we are doing when we're out on site. We just did this in our office kind of to be able to show. So I'm gonna play a quick video. This is the interface for the data acquisition system, but basically we're starting to record. Jack's gonna do what we call the jump test. As the name implies, he does a little hop. There you can see the acceleration. And he starts the floor kind of vibrating. You can see here in a second. So there's the acceleration history on the left. There's the jump, and then it decays quite quickly. So from that we can measure damping. And then on the right-hand side is our friendly Fourier spectrum. I told you it would be useful if you were paying attention earlier when I was talking about the vibration theory. But from that, we can identify the peaks on that, tell us what the modes of the floor are. So for this floor, there was a mode at about, you can see in green there, about 4.6 hertz, and another mode at like 7.2 hertz. So that's helpful again for when we look at our analysis model of the floor, we can see, does that align, or do we need to adjust our model, and how? And then from that, we can say, okay, well, again, we remember about our harmonics. We know that the fourth harmonic of 1.8 hertz, 4 times 1.8 equals about 7.2. So 1.8, that's a pretty comfortable walking pace. You can sort of set a metronome to that and try walking at it. That's a pretty comfortable walking pace. So what we're going to do next is have Jack's going to walk. He's going to actually put a metronome on, and he's going to set it to 1.8 hertz, and he's going to walk at that speed around this accelerometer and really try and get, I know the video is small in the upper right-hand corner, but he's going to really try and get this floor excited. Jack's good at exciting floors, I guess one could say. So he's walking around. We're measuring accelerations to super high sensitivities kind of in real time. And from that, that's where we can say, is the floor good, or how good is the floor, both in terms of peak or acceleration, or this root mean square velocity. And we can compare that against those thresholds that Jack talked about, which are, what is a typical residence? What is a luxury residence? And when we're doing this, what we've done for many of our buildings around town, we've been able to say, like, how good were our analysis models, not just at predicting the modes of the building, meaning what the modes look, the mode shapes and the frequencies, but how good was our design process at predicting the performance, the acceleration and velocity performance. And I'll say vibration is tricky. I think we are fairly good at predicting frequencies. We are less good at predicting acceleration velocities, but thankfully, humans are sensitive and subjective when it comes to vibration. So it's not like if you're at, like in this example, we're at 0.7% G, we would say a typical office criteria would be 0.5% G. That is not like having a DCR of like 1.2, that is not like imminent failure. That is probably imperceptibly different between 0.5 and 0.7. If this was like 0.5 was our criteria and we were getting at 1% G, that would be noticeable. So we kind of think of vibration in terms of this, like when you double things, that's when kind of the perception of it dramatically changes. So kind of to conclude, we talked about the sensitivity and subjectivity of vibration, how it's not a code requirement in the US, but is an important design consideration for mass timber floors. And as we get to longer spans or seek longer spans, often is the governing design criteria. I went through a little of the vibration theory that we kind of need in context to understand vibration for mass timber floors. Jack spoke to us about the limits, the typical kind of agreed upon limits or industry standard limits for human and equipment thresholds for vibration. He talked through some of the design decisions, kind of the 4 things that we can play with: stiffness, mass, damping, and vibration path, and how we can kind of use a combination of those to get to the desired performance level. And then he went into detail in the methods, analysis methods and modeling approaches. And really to date, unless you're doing a CLT bearing wall structure, really you're down the path of this modal combination procedure. We didn't go through the details of how to do that, but a lot of that's illustrated in the mass timber floor vibration design guide. Would reference you back to that. Please read it if you have interest. We talked through a couple of those design examples, which give you context kind of in the mass timber realm of the type of buildings that we typically design and how vibration could be analyzed for those. And then walked you through a little bit of how we're trying to benchmark all of the previous stuff in the real world via testing. So I think with that, I'll just leave up here. Here's our email addresses if you have questions. And then I think I turn it back over to you, Evan, if that's the right approach.
Yeah, great. Thanks, Reid. Thanks, Jack. Yeah, no, we can just open it right up to questions. So if you have a question for Reid or Jack, please just go right for it. And if you prefer to put something in the chat, I'm happy to ask for you. So Reid, you've got one from Graham Montgomery there if you want to. So Graham asked, you mentioned in the beginning of your presentation that RMS acceleration is more accurate to what humans feel. Why are all recommendations referencing peak?
Yeah, it's a good question. So this predates me a bit, but if you look to ASC Design Guide 11, there's a figure in there, and I'm forgetting if it's peak or RMS acceleration versus frequency. And if you look in there's a ISO criteria. If you look in that, it has the opposite. So one has peak acceleration versus frequency, other has RMS acceleration versus frequency, but the actual curves are identical, even though we know that there's this square root of 2 difference between them. And one of our colleagues in our Seattle office is trying to figure out what exactly is going on here, why those 2 figures could be identical but have different vertical axes. And the answer he basically got was, well, in vibration, that 0.7 factor, which is 1 over square root 2, isn't enough to matter. So we just changed it from peak to RMS. So absolutely, peak doesn't make much sense. And it's especially in the context of when you're going out and testing it. You know, an individual footfall can cause a fairly decent high peak, but then like sitting there, people don't really feel that, or are not, perturbed as much by that individual peak as they are by someone continuously walking next to them. Typically, someone's not like walking directly around you in a circle like Jack was doing in the tests, But if you say you have a spot next to a hallway or next to a corridor, you can have pretty continuous walking next to you. So I think it's a little bit of product of that history of kind of this, peak versus RMS and on that threshold plot. But we have an opportunity, I think, in mass timber to, as we've done in the floor vibration design guide, to kind of reset things to the more appropriate terms. And I guess, at least in my opinion, I won't speak for others, RMS is the right approach. I hope that answered your question, Graham.
I'm curious, how much do other forms of excitation play into sort of these calculations that you guys make, like say from a large truck that drives by a building or something like that?
Yeah, it's a great question. So yeah, you have to be, how do you say, you have to define your space a bit when we're giving these types of presentations. So we specifically had that human induced in the title. And human-induced walking, even, I guess that's a even further clarifier, where I guess we're only really talking about pretty limited scope here today. So some of the other things that cause vibration in structures, which can be important, particularly mechanical equipment. Generally, in modern structures, mechanical equipment which generates vibration, basically anything with a spinning part. If it's slightly out of balance, right, it induces essentially it's an eccentric oscillator. Almost all of those are vibration isolated in modern buildings. So generally those aren't significant sources of vibration in the frequencies that humans are sensitive to, which is that 4 to 8 hertz. Another one, obviously being vehicular traffic or train traffic. Again, generally, Jack and I have been out testing buildings where we like to do an ambient test, which we didn't show you a video because it's pretty boring, where we just set up on the floor and we measure for 30 seconds just to see the ambient movement of the building, which can be as something as minimal as people opening and closing doors or any of the vibration that gets through the vibration isolation of mechanical equipment. And it's very clear when a truck drives by, especially if it's a pothole, you can see it in the acceleration history. Generally, though, that's at a threshold that is at or below human perceptibility. Jack and I also recently tested, Jack set out for several hours waiting for a train at a building. That is a different level of excitation and can equal or exceed that due to human-induced walking. But primarily in structures, it's your fellow coworkers walking by that cause the biggest issue. The other thing, maybe the last thing before I stop talking here, is rhythmic activity. If you have exercise space, a dance studio, something like that, and multiple people jumping at the same frequency, especially when that dance frequency corresponds to a harmonic of your natural frequency. Again, another test that Jack and I did where we were worried about that. He and I were doing jumping jacks. I had to keep up with him, but he and I were doing jumping jacks at a set frequency to try and hit that harmonic of the floor. And that can produce also very high accelerations and velocities. Again, very high in the context of human perception, but not, again, in the context of really damage to structure.
Gotcha, thanks.
I had a question about the modeling. might be getting a little bit into the weeds, but I was curious about how you apply that, the force of people walking to your model. Is it essentially saying like there's a bunch of people marching all over this floor plane and it's being excited at a certain rate, or how do you actually apply that to your model?
So I think what you're thinking of is what we would call a time history response analysis, where the loads are actually applied in the model over a period of time, and we're actually using the model itself to produce our response plots and velocity and accelerations. But within the modeling that I showed, we're not actually applying loads, the footfall loads within that SAP model. We're just exporting the modal response of the structure. And then within the post-processing equations, that's where the kind of simulated footfall loads are applied.
And maybe so that those in the Excel sheet, they're actually using that information to get your acceleration.
Yes.
The analogy that strikes more, I would say, vibration wasn't something that at least structural vibration wasn't something I spent a lot of time on in school. But the parallel that I like to think of specifically with analysis, as Jack mentioned, is the parallel with like lateral design, specifically seismic design. So the modal combination method is the equivalent of response spectrum method, whereas the time history method, it's kind of the same in seismic design and in vibration, where you're actually applying the history. But the modal combination method is kind of like response spectrum method, but for vibration. And really, you only out of the analysis, all you need.
I was trying to connect those two. That helps.
Yep.
Thank you.
Have you guys ever worked on a project where you needed to purposefully induce sort of heavy sense of vibration? I am specifically thinking about the Crystal Ballroom in Portland. I know you guys are up there. I don't know if you've ever been there before. Yeah, it's like a spring, sort of like purposefully springy, spring-loaded floor. And it's, if you don't know, it's absolutely terrifying when a bunch of people are dancing on it.
Yeah, Katie and I were there with our spouses for a concert. Who was playing, Katie? Do you remember? At the Crystal Ballroom?
I don't actually remember. I've been there for actually a marching band concert though too.
Yeah.
Was it that concert?
Yeah, it was
the one that Spencer goes crazy for.
Yes.
Was it was it an actual marching band, or was this March 4th?
Yeah, it was March 4th.
I saw March 4th there at the Crystal Ballroom. It was interesting. Yeah.
We might have been there at the same time.
Yeah, we might have been.
Yeah. We have never purposely induced vibrations to that for a floor, other than our jump tests. We have done, I guess, the opposite, which is where we have retrofitted floors for vibration using tuned mass dampers, which Jack talked about. Again, those four things: stiffness, mass, damping, vibration path. It's hard to adjust damping in the context of the typical structural materials, but where you can introduce a designated damper or a small tuned mass damper. We just finished a project, not on a mass timber floor, but on a steel frame floor, using tuned mass dampers to suppress vibration. And it has a big effect. Like we had like a 60% reduction using tuned mass dampers. But we see that more as a retrofit solution. And thankfully, we haven't had to retrofit any mass timber floors yet. But I do think that's something that, the idea with the interesting thing with mass timber is that kind of every mass timber office and residence becomes at least sold as luxury. So there's a little heightened perception, even if that floor is bouncing the same amount that a steel or a concrete floor would be. It's kind of the perception that you're in this high luxury space. And so it would not surprise me if we see need for vibration measurement and kind of a reckoning of expectations around vibration in mass timber structures.
Yeah, unless it's branded as it's cool to have a little bit of that excitation, it's
Yeah.
like blue jeans or something. That's the bonus you get.
Yeah, I know that, we used to work in a steel framed office building, and definitely some people walking by, there's certain people who are, we would say, heavy of foot, that you're like, oh, that person's coming. I can feel them coming. And I wouldn't say our floor is especially bouncy, nor is it especially like high performance. But yeah, the fact of how different people perceive it, how different people affect the floor, even someone who's, you would think like, oh, it would just scale with mass. It absolutely doesn't just scale with mass. Some light people can be quite stompers. Not Jack or Katie. They're great. They're quite light of foot, but others.
And so that's interesting. You were saying in the beginning of the presentation that the gut, did I interpret this correctly, is the most sensitive in terms of like our bodies, in terms of perceiving. So it's kind of like we have these built-in accelerometers in our bodies, and the gut is kind of the core accelerometer or whatever in our body that detects these vibrations in the 4 to 8 hertz realm.
Yeah, I don't know exactly how it was established. I mean, there's a lot of research on this for astronauts, right? Because if there's a certain frequency that corresponds to a part in your body, and they're experiencing obviously much higher levels of acceleration, that can cause actual damage, human damage, right? But my understanding is that, yeah, it's that we're uncomfortable in that range because our gut is vibrating. If our gut gets vibrating too much, it starts slamming into our rib cage, and that's where we die.
So that's not a good way to go.
No, it's not.
Interesting though. Wonder if that was like a biological evolution to detect, big saber-toothed tigers coming from behind or something, or
I don't know.
Well, they'd probably be pretty light of foot as well, I guess.
Yeah, I think all of the prehistoric measurements of saber-toothed tigers sneaking up on people, none of those records survive today for some reason.
This is a good future avenue of research.
Right.
All right. Well, I'm taking up a lot of questionnaire here. Anybody else have a question for the panelists?
One more here. Have you looked at all about like kind of component level vibrations versus system level, and are there any issues that are like specific to others, or do both kind of come out in the wash when you do your modal analysis of the whole structure?
I guess can you clarify what you mean by component versus system?
So say looking at one panel versus an entire floor system, and yeah, are there any issues that are certain frequencies, or I guess issues that come up when you're just looking at that kind of micro scale?
Yeah, I can talk to a little bit, and then Jack has some thoughts on this as well. But yeah, it's usually in the design process, you're absolutely trying to kind of decompose which mode is governing, which you can start to see a little bit by not by intuition, but you can see in those plots that Jack was showing in terms of where the peaks occur and which harmonic governs. If you multiply that that frequency at which the peak occurs by the harmonic number, you can find the mode that's governing there. And then it's usually of interest to say, is that a panel mode? Or if it's panels spanning to beams, is that a beam mode? Is it a girder mode? So you can know how to target specifically you're doing stiffness, where to put the material that's best used. I don't know, Jack, you have anything else to add on that?
I don't think so. I mean, I know we did some smaller scale testing on the Catalyst building. I think I see Hans Eric on the call, and he was leading that effort, testing individual CLT panels with glulam beams on the component scale. But we were more kind of focused on the global kind of full bay, larger system, because if you add more components, you're just going to increase the flexibility of the system, and it's really generally that lowest fundamental frequency of the entire bay that we're most concerned about.
Gotcha. Makes sense. Thank you.
All right, do we have any more questions? Reid, Jack, Katie, do you guys have any kind of last comments or anything else you want to share?
I think just say that remember, whenever you're designing a mass timber floor, to not wait to think about vibration as an afterthought, because particularly for higher end offices and residences, like I said, which is kind of the perception of all mass timber buildings, is that it can govern and will govern and can have an effect on cost. And if you can get in front of the owner and ask them about what their vibration tolerance is, usually that becomes more of an educational exercise than it does really them saying like, oh, I want a 8,000 microns per second floor. But doing that, I think, just sets expectations so that you can actually design to something real, and you can have kind of a floor that performs well, but not have to just, as Jack mentioned earlier, throw cost at it. That's the way to essentially price out mass timber and price in concrete or steel. And other than that, I think just say thank you to all for joining here on what's turning out to be a little bit of a rainy day. Thank goodness it's raining again. And yeah, thanks for joining us, and reach out if you have any questions.
Yeah, thank you guys so much. We'll give you a virtual silent round of applause here, but really appreciate you taking the time to come speak with us, and we're looking forward to your next presentation, whatever it may be. Yeah, for everybody else who's remaining, maybe see you September 9th for our mass timber meetup on modular housing with aspect and thin. So have a good night and see you next time.
Thanks all.
Thanks for having
Bye.
us.
Yep. See ya.